Let us do a problem, a proof to get our hands around the concept of Cartesian products and how they work. So say let A and B are two sets and they are given that A and B are listable sets. Well, this is a term I made up, so this is not actually called listable in further mathematics, but this should be a fairly intuitive explanation for what I want to do. So I'll use this property later. I'll let you know what listable means later, but for now let A and B be two sets. Show that sets A cross B and B cross A. So these are two sets I can form using A and B by applying the cross product operation. So let the sets A cross B and B cross A have an element in common. Alright, so immediately I know that A cross B and B cross A are different sets, because if A and B are different, say A and B are at least one of the elements is different, then A cross B would be the set of all ordered pairs where the first entry is from A and the second entry is from B. So x comma y would belong to A cross B. If that's the case, then y comma x has to belong to B cross A, because of the nature of cross products and ordered pairs. So these both will be different sets. So we'll have to show that A cross B and B cross A, if they had an element in common, then so that will happen if and only if. So this is called if and only if. It's a symbol for it, IFF. And if and only if, what it means is if this statement happens, then this has to happen. Whatever the other statement is, we'll go over it. So if this happens, then this has to happen, and the only way of the first statement happening is that the second statement would have happened. So we also prove the reverse implication, that is, if the second statement is true, then the first statement would also be true. If we prove both the implications, then we can say that the first statement happens if and only if the second statement happens. Okay, so let me go over the second statement. So show that we'll have to show that A cross B and B cross A have if they have an element in common, if and only if the sets A and B themselves have an element in common. Okay, so A and B are different from these sets, and if A and B have had an element in common, only then this would have had an element in common. Alright, so let us prove, we do need to prove implication both ways. So at once, just observing the second statement, say that the second statement is true. So say that A and B have an element in common. It should be fairly obvious that A cross B and B cross A would have some element in common. So let me write down what I mean. Let me write it down formally. So say A cross, or say let A be this set, x1, x2. It might be infinite, but now I'm using the property of A being listable, right? So I'm using this property. I can list A in any given order. So I can list A, and I can still call this an infinite set, but I can still list it. So this is important for my proof. Later we'll make a remark about that also. Okay, so if A is this set and if B is some other set, so let me use another variable to denote the other set, y1, y2, y3, and it goes on forever, or maybe it is finite, I don't know. So it's a bunch of yi's, if you will. And what have we assumed? We have assumed the second statement is true. So we have assumed that A and B have an element in common. So maybe I'll give a name to the common element. Say my x94 was common, or x100 was common. So I'll call it k. Let sum xi be equal to k. So maybe I'll write xi is equal to k for some I. For some I. All these notations come from our mathematics reasonings playlist. So and I'll have to take that k itself in my set B, because I need some element that has to be common. So let yj be k, some yj, I don't know which one, but some of yj, one of the yj's would be equal to k, right? So for one of j's that will be true. Okay, so what do we get then? What about A cross B? A cross B would be the set, so let me write it in the set builder form itself now. So it will be the set xi comma yj, because I'm taking all the possible ordered pairs I can take, and where I and j both are natural numbers. So for I and j belong to natural numbers. And what about b cross a? Well, b cross a would be the set yi comma xj, or I could have used a different script also here, but fine. Yi comma xj, where I and j belong to natural numbers again. That is, I am taking yi's from b and xj's from a this time, just the other way around. So just the opposite kind of what I did for a cross b. But what will happen when there will be some element here in the ordered pair that will be k comma k, because some xi is equal to k and some yj is equal to k. So for that number we'll have a k comma k in a cross b, and a similar argument can be given for some element in b cross a being k comma k. So we have assumed that a and b have an element in common, and that is k. So the cross product or the Cartesian product have k comma k in common, and that's what we wanted to prove. So at least the first implication is covered. This implication is covered. You may rewind and watch if you're not clear with the logic, or you may pause and ponder upon it. So we'll have to prove this implication now, whether this is true or not. So we'll assume that a cross b and b cross a have an element in common, and then we try to prove, assuming that that is true, then we'd show that there will be a common element, at least one common element in a and b. So let me say that let a cross b and b cross a and b cross a have a common element, and let that common element be, so because there is a common element, I'll give it a name. Let that common element be m comma n. It need not be of the form m comma m as we saw before. There might be some random m comma n that is common. So m comma n, let it belong to a cross b, as well as m comma n belongs to b cross a. So I always have a problem saying b cross a, I don't know why. Okay, so what does that mean? So by the nature of ordered pairs, by the nature of Cartesian products, what this means is, this implies that m has to belong to a, because m has to have come from a, and n has to have come from b. Similarly, this statement, this also has to be true if these have an element in common. So I'll put an and here. So this means that m has to have come from b this time, because m is the first entry, and n has to have come from a. So now if we just look at this criteria, it will be very obvious what are the common elements in a and b, because if, what have we done? Because if this is true, then this would be true, then this would be true, and hence m would have belonged to a as well as m belongs to b. So we already found a common element, we are done. So m belongs to both a and b. Hence we have proved the fact that a and b have at least one element in common. But the way we have written it, n will also be another element, and you might take some examples and think about the fact what would happen. But let me just go out and say that if the common element is of the form m comma m, then you'll get a single element common in a and b. If that's all that is common, you'll get a single element common in a and b. And if something like this, where m and n are different, is common, then m and n both will be common to a and b. So I hope this proof helps. You should really try to figure this out on your own. Sit with a few examples of a, b and a cross b and find out if this holds or not.